Hello, today we'll control a Nema 17 stepper motor with an A4988 driver along with an Arduino. To start working, we need to set the current limit for the stepper motor, which is done by setting the reference voltage, that is Vref, on the driver. For the A4988 driver, the formula used is Vref equals Imax multiplied by 8 and multiplied by RS, where Imax is the maximum operating current of the motor winding and RS is the resistance of the current sensing resistor on the driver board. First, we find out the motor current. For this, we go to its datasheet and look for the value rated current or current. In my case, it equals 0.7 amperes. Now, we find out the resistor resistance, RS, by looking at the marking on the driver board. In my case, it says R100. R is a decimal point and 100 is a number after the point, which means that the resistance RS equals 0.1 ohms. Next, we calculate Vref using the formula. I recommend that you take not the full rated current, but only 80% of this value. This is necessary because excessive heat may be generated by the driver and the motor itself, and there may be inaccuracies in the resistors. So we take 80% of 0.7 amps, which is 0.56 amps. Now we multiply this value by 8 and multiply it by the resistance of the resistor, RS, which, as we have determined, is 0.1 ohms. As a result, we get 0.448 volts, which must be set on the driver. To set the reference voltage on the A4988 driver, we need a screwdriver, 2 crocodile clips, a multimeter, a power supply, and of course the driver itself. Take the screwdriver, attach one end of the first alligator clip to it, and attach the other end of this alligator clip to the positive probe of the multimeter. Connect the second alligator clip to the negative probe of the multimeter. We connect its other end to the GND pin on the A4988 driver. Now we supply a logical 5-volt power supply to the VDD and GND pins on the driver. After that, we turn on the DC voltage measurement mode on the multimeter. Begin to carefully turn the variable resistor on the driver, touching its metal part with the screwdriver, until you get the reference voltage you need, which in my case is 0.448 volts. Your driver is now configured and ready to be connected. First, we connect the DIR pin or direction pin to one of the Arduino digital pins, for example D2, and the step pin to another digital pin, for example D3. Now we connect the reset and sleep pins together to use the internal pull-up resistor of the sleep pin, which supplies a logical 1 to both pins, thereby bringing the driver out of sleep and reset mode for immediate operation. Then we supply 5 volts to the logic part of the driver by connecting the VDD pin to the 5-volt pin on the Arduino and the GND pin to the GND pin on the Arduino. For stability, we also connect a 10 microfarads electrolytic capacitor. The next step is to connect the stepper motor itself to the driver board. To do this, connect the 2 groups of motor windings to the first and second groups. There are 2 ways to find out which group is which. The first is the simplest. You will only need one jumper and the stepper motor itself. First, try to rotate the stepper motor shaft with your hand. It should rotate quite easily. Remember how easy it was to rotate? And now take your jumper and try to short circuit the 2 terminals of the stepper motor windings. After that, try turning the motor shaft again. If the feeling is not significantly different or has not changed at all, disconnect one jumper contact from the winding output and connect it to the other contact. Repeat this procedure until the motor shaft becomes significantly harder to turn. Now separate these 2 outputs from the other contacts and connect them to the contacts of one of the groups, namely 1 or 2. Let's say I connect them to group 1 and the other pair of contacts to the other group. I will say right away that if you connect these contacts in reverse, for example, the stepper motor will simply rotate in the other direction. The second method involves using a multimeter. Turn on continuity mode, take 2 probes, and connect both of them to any contacts. Then move one of the probes between all the contacts until the multimeter starts beeping. As mentioned earlier, connect it to the driver. The last step is to supply power through the driver to the stepper motor. To do this, connect the VM pin to the power source required by your stepper motor. In my case, it's 12 volts. And the GND pin to the negative terminal of the power source. Also connect the capacitor here, which significantly stabilizes the power supply for the stepper motor. Its capacitance should be at least 100 microfarads. After connecting the main circuit, we need to set the rotation accuracy or step division. Microstep control is performed by 3 pins, MS1, MS2, and MS3, short for Microstep Select. By combining a 5-volt supply or ground to them, we can change the number of steps per motor revolution. For example, if your Nema 17 has 200 steps per revolution, these settings will increase it. Here are the 5 available division modes for the A4988. For a full step, connect pins MS1, MS2, and MS3 to ground. The motor makes, for example, 200 steps per revolution. This is the default mode if the pins are not even connected. If you want half a step, connect pin MS1 to 5 volts and MS2 and MS3 to ground. The accuracy increases 2 times to 400 steps per revolution. To get a quarter step, connect pin MS1 to ground, MS2 to 5 volts, and MS3 to ground. Now we get 800 steps per revolution, which already provides much smoother movement. If you need an eighth of a step, connect pins MS1 and MS2 to 5 volts and MS3 to ground. Now you have 1600 steps per revolution. If you need 1/16th of a step, connect pins MS1, MS2, and MS3 to 5 volts. As a result, you will get maximum smoothness of 3200 microsteps per revolution. Before we start writing code, we need to install the AccelStepper library through the Library Manager. To do this, go to the Library Manager. It's the icon on the left that looks like a book. Type the name of the library in the search bar and download the latest version of AccelStepper for Mic. Creating a control program begins with initialization. The AccelStepper library is connected, contacts, pins for control are defined. The number of steps per full motor revolution is calculated, and the main control object is created. In the initial setup function, important movement restrictions are set. The maximum speed is set, as well as the smoothness of acceleration and braking. In the main program loop, the movement is performed in 2 stages. First, the goal is set. The exact number of steps that the motor must take is specified. Then the movement is performed. There are 2 main approaches to this. Blocking, when the microcontroller waits until the motor completes its entire journey, and non-blocking, when the control function must be called continuously in a loop. The second method allows the program to generate step pulses only when necessary to maintain the specified dynamics, speed and acceleration, until the distance to the target reaches 0. After uploading the code, don't forget to attach the heatsink that usually comes with the driver if you want to prevent overheating and extend its life. As a result, we get the rotation of the stepper motor shaft, the speed and direction of which we can change in the code. I really hope that this video has helped you understand how to control a stepper motor. As always, I will leave the code and connection diagram in the description below this video. Thank you for watching and good luck with your projects.